thank you for the kind invitation. It's been an honor to attend this really nice symposium so far. So I would like to talk about self-monitoring of timing in humans and rats. We could ask the first question, which wouldn't be really appropriate here because we know, like, that's already been answered, that the brain can time. More appropriate question for my talk would be, can the brain time brain timing time? So this will be the main question we'll address today. And first, I will talk about self-estimation of timing errors in humans. Then we'll switch to rats. And then we'll cover some recent results that try to dissociate timing and and monitoring of errors in humans and then rats. So in the lab, we can measure timing ability very, very simply. I think it's one of the simplest timing tasks. So in time production task, we ask participants to produce a time interval, say 2 seconds. So imagine that you initiate a stopwatch by pressing a button once, and you terminate the interval by a second press, and the goal is to approximate the target duration as close as possible. So let's try it together. I'll give you a cue. I will clap, and you start your internal stopwatch, and when you think that 2 seconds have passed, raise your hand. Okay. So now you experienced one trial in our task. You may have also noticed that when you look at your neighbors, that there was a variability. You didn't raise hand at the same time. So this is one of the main features, and of course it was covered before, that there is variability of the timing performance. And the question is whether, to what extent, the brain represents also that variability. So in timing literature basically focuses on point estimates. We try to explain why certain duration is perceived as short or long, and there is plenty of beautiful work showing sequential activity, showing ramping cells, showing timing cells. All that can reproduce this variability. We can fit with these models the distributions, behavioral distributions. We can model the uncertainty, but I would like to go beyond that. And already there was a suggestion in the literature already that besides current duration representation, the brain may also represent temporal distributions and have knowledge of temporal uncertainty. So let me quickly give you an example of that behavior. So in a task where a rat has to space 2 responses by minimal amount of time in order to receive a reward. So whenever this duration between the 2 presses is, let's say, longer than 2 seconds, they will be rewarded with a pellet. So in this simple task, what we can see that rats they produce a distribution of responses that peak just after the time t. There is few responses that are premature, and essentially most of the time they would get a reward. Now, if you look at across rats or across sessions, what you will see that the closer the mean of this distribution is, the smaller the standard deviation of that distribution is, suggesting that rats do perform optimally in that task. That basically suggests that temporal representations may be rich and probabilistic as humans, rats, and mice take into account their own uncertainty. So we wanted to push it a little bit further in that we asked whether can we introspect about our timing error. So for that, we constructed a new task where after each time productions, participants judge the direction and magnitude of just produced time interval. So it could be too short or too long. So let's try it together. I will give you a cue again. You do the same task as before, and then I will ask you a question. And now you can ask yourself whether you were slightly too short or slightly too long. So that's essentially what participants do in our tasks, and now you experience one trial from our experiment. So if the error in time production is viable, then the estimated magnitude of timing errors should correlate simply with time production. And that is exactly what we see in our tasks, showing that the ability to accurately report timing errors, and we call it temporal error monitoring, basically. So it shows that participants have some degree of insight into their own performance. You could ask whether it is timing that participants monitor, or it's perhaps just a motor execution. So we run a quick experiment under the assumption that variability in motor timing consists of variability in clock variance and motor variance. And participants had to execute their time productions by pressing or by moving a joystick. So in the situation where you move a joystick, you increase motor variance. And the prediction is that in the move condition, if participants only monitor the clock variance, their error judgment performance should be actually worse. So basically, we would disrupt participants' error monitoring by adding motor variance. So what we find is that actually, surprisingly, but nice for our line of research actually, is that they perform better under the press condition. So that simply suggests that what people monitor in this task is something that could be accounted for clock variance rather than motor variance. So the first conclusion is that the brain may possess a mechanism for evaluating the state of duration representation. Now, let's try to switch to rats. As it's also nice if you can have model with which you can interact a little bit better if you want to find neural basis of behavior. So that was first motivation. But the second motivation is simply interesting on its own, that whether rats could have similar behavior as humans actually. So the question is how to ask rats about their timing errors. So for that, I constructed a novel task in which first I trained rats to produce time intervals like humans did, with only one difference, such that they were rewarded for all time productions longer than the target duration. So for each individual rat, now I plot a distribution of time production aligned to the second press. So as the goal was to train rats in reporting their own timing errors, we first estimated for each rat a threshold that divides small error time productions from large error time productions. You see individual thresholds around here. And I use these individual thresholds to design a reward assignment rule, which was based on distribution of time production for each individual rat. So now we classify time productions from each rat as small error time productions in green and large error time productions in orange. So the small error time productions were only rewarded in a small error port, and the large error time productions were rewarded in the other port. So here is example trial. Rat is producing duration, and then they are cued to go and pick reward or not, to either they receive reward or not, depending on the duration of that trial. There was a trial that was too short, so no light. There is one that was in the range, so again they receive a cue, and they can perhaps pick the port. So already at when we looked at those training trials, we saw that we saw effect of reaction time, so how fast they go in the port, based on whether the time production corresponded with the port that was lit up. So when so basically when the port was congruent with the time production, they would go faster there because they were anticipating pellet coming in that port. So that was already a cue that they may have the insight in their own time productions. But there is more explicit way to assess that, and simply what we did, we have test trials where we light up both ports, and then rats can choose themselves which port they want to go to and where reward should be. So here is one example. One rat is doing a time production, and it was a test trial, so he had to choose. Also, in terms of a movement strategy of the movement, it was really outlier, and his performance on error judgment was really, really bad. So if someone thinks that associating movement with error judgment could be the solution to what I'm presenting, it's not the case. He was one of the worst ones. So we can see now a low probability of choosing a large error port when the error in time production was small, and we can see that the probability is increasing for long error trials, basically. We can also replot the data in terms of accuracy, and what we see is that each rat on most of the sessions have accuracy that is higher than 0.5 because we had 2 ports. So you see that as a group, our population of rats performed pretty well, on average reaching the accuracy of 65%. So to sum up, we establish here a paradigm in which rats, as humans, do monitor and report magnitude of their timing errors, showing self-monitoring abilities. An additional analysis I will not go into now showed also a richness and complexity of information that rats represent in this task. So now we have a task that kind of works in both humans and rats, and the question here was, well, we would like to start to investigate the neural basis of that behavior. So, very simplified hypothesis is that when we monitor temporal errors, we should be able to dissociate the clock from a mechanism that reads out those errors. So overall working hypothesis that we have is that we could dissociate time production from error judgment. So what mediates accurate timing error reports? So first we moved into humans, and we in this first experiment, Dunya used transcranial direct current stimulation that basically relies on applying constant current throughout the session through the skull of participants. We can have anodal or cathodal form of stimulation, and overall assumption in the literature is that anodal stimulation would increase the probability of firing, whereas the cathodal stimulation would decrease the probability of firing, but that may be a little bit more complicated. I will come back to that later. So we used TDCS, and we, from the previous studies that I conducted using MEG, we found prefrontal and frontal-central regions to be involved in that task and in monitoring of temporal errors. So what we did, we applied the current using those two montages. This is the nose of participants, this is the anode, this is the cathode, and so this is the montage for PFC, this is the montage for FCC. Those were same participants, but two different days, and we also had a sham session. Below you can see the spread of the current with the simulation. You can see that those are two non-overlapping distributions with PFC and FCC. Overall, the task remained unchanged, with one addition such that after the error judgment, we also asked participants about their confidence of their time production. So that was a small addition here. And so under the hypothesis that we could dissociate time production and error judgment, we first looked at participants' time productions. And what we basically see is that in neither PFC or FCC stimulation, time production distributions remained unchanged. So far, so good. So now what happens with their error judgments? So what we see in FCC is that the stimulation did not affect participants' performance, but we had quite solid effect in PFC group. So it's the one that is more frontal. And here you can see that actually under the TDCS stimulation, their error judgment follow time productions more faithfully. So we actually did not interfere with their performance. We enhanced their error monitoring performance, which corresponds to some other effects that people find with TDCS, improving working memory and other tasks. So it's not totally weird. And to convince you a little bit more that we really have the effect here, what I show you here is actually, instead of correlation slope, we basically look at the distance between time production and error judgment when we normalize the two scales. So if their error judgments are more accurate, what you should see is that this index of accuracy should be smaller for TDCS condition, and that's exactly what we can see here. In terms of confidence, in line with the previous data, we found that in PFC condition, the relationship between error judgment and confidence judgment was improved under the stimulation condition. So to sum up, stimulation of prefrontal areas improves error monitoring of temporal errors. So in a way, what we can do is basically improve participants' insight in their own time representation. I will briefly mention my previous results, where I found that beta power correlates with produced time intervals, such that when this is the first press and this is the onset of the time interval, looking at the first 600 or 800 milliseconds, we can basically distinguish short time productions from long time productions. And it was the finding from my PhD then actually I wondered that if this is something that is really related to timing behavior, if we look at accuracy of error judgments, there should be something in those beta oscillations that would tell us the accuracy of participants' performance. So if we then squeeze these beta oscillations and do PCA on it, what we see is that those beta oscillations are more or less separated for different participants. And degree of this separation then predicts participants' error judgment accuracy. So, given the finding on the PFC that we just obtained, what actually the hypothesis is. In the recent paper, there was suggestion that actually TDCS improves, enhances the oscillation in the theta band. So what Dunia is doing now, she's collecting simultaneous EEG and TDCS data to see basically if the effect that we find can be somehow attributed to the communication between PFC and perhaps those beta states that I just showed you. So now let's switch quickly to rats. And analogically to humans, here we can be a little bit more accurate about locations. In very similar, almost unchanged task, we had two groups of rat where we injected mucimol. We targeted orbitofrontal cortex and anterior cingulate. We looked at OFC because of big literature about confidence, and there is a little bit of literature in ACC that relates to error judgments also. So first we train rats on the task to really good degree. Then rats went through surgery, implantation, retraining, and on alternating days we were injecting mucimol and saline in the same rat. That also allowed us to replicate the previous finding with just one modification, such that instead of 2 pellet and 1 pellet for short and long intervals, now we reward rats with 1 pellet in both ports. You see that the same behavioral effects as before, such that as time production is increasing, the probability of choosing long error port is also increasing. Here we can see across multiple sessions and across multiple rats their accuracies. So we can basically see that they perform quite well. We had 24 rats, and we had 12 rats per brain structure. So inhibiting OFC impaired rats' ability to produce time intervals compared to control conditions, as evident in the increase of the in green standard deviation with respect to the time production. Basically, they were severely impaired in terms of how they could keep track of time, which to the extent that it really prevent us from investigating their error judgments. Contrary to OFC group, in the ACC group, timing performance was not impaired, analogical to the results that I showed you with humans. So you can see, you can appreciate nicely overlapping distributions under control condition and mu-simul. Same slopes for the regression that fits coefficient of variation against time production. So I think that's pretty convincing that nothing happens with time production under mu-simul when we inject in ACC. However, under the hypothesis that ACC is involved in error monitoring but does not impact timing, we are expecting to see that probability of choosing long error port as a function of time production would be affected. And this is exactly what Lea found, that the effect of probability of choosing long error port given their time production differs between saline and mu-simul, such that sensitivity is not affected, but there is an overestimation bias to judge produced duration as longer under mu-simul. So that's exactly right here. So in terms of a timer and reader hypothesis, what we can say is that ACC inhibition did not affect the timer, as all the properties of time production remained unchanged. And the shift in the psychometric curve means that the threshold that maps choices to short error and long error was affected actually. So it differs slightly from the effects that we find in humans, but the thing that is in common is that we can really dissociate time production from error judgment. So to sum up, OFC is needed for time production generation through modulation of impulsivity or perhaps effort. And in ACC temporal, we can see impairment of temporal error monitoring. We also found something that is related, that it could be a classic finding for ACC, and so that means that we find inability to adapt to negative feedback also. And so to sum up, the key findings is that humans and rats monitor their timing errors, demonstrating richness of their duration representation. And this work established the first correlates of the ability to monitor temporal errors in rats and humans. And finally, duration representation and itself monitoring can be dissociated, suggesting metacognitive architectures for time. I would like to acknowledge Sena, Lea, and Dunya for all the work on humans and rats that they did, and my collaborators, Valerie, Virginie, and Sylvia, and also National Science Center in Poland that provide the funding for this research. Thank you.